So you have seen that integer programming is NP complete even under great restriction. So let's do this arithmetization more. So another example or another way to arithmetize CNF. Right now we used inequalities. I'll now do it without inequalities. Another way to arithmetize CNF without inequalities. Let's do that. The result is quadratic equations, solutions of those. So S is a system of quadratic equations modulo 2. Okay, so these are n-variate polynomials, degree 2, and you are only interested in again 0, 1 solutions, but the arithmetic is really a modular arithmetic, mod 2. And S has a root. So now the this problem, it's like SAT, but it's very algebraic because we are actually looking for a root, mod 2 root of an n-variate quadratic system. So this problem is also NP complete. Okay, let's prove this. So in general, finding solutions or roots of polynomial systems, that is hard. Okay, these things are really NP hard, and here is your very special example. These are just quadratic equations mod 2, even that is NP hard. So given a point x in this finite field of 2 elements mod 2 to the n, given this 0, 1 point, it's easy to verify whether it's a root. Whether x is a root of S. So this means that quadratic equation 2 is in NP. Okay, so if there is a root, it's a 0, 1 root, somebody gives it to you and you can verify fast. So that is what this NP condition is. So now comes the NP hard part. So for any 3 CNF phi, we convert each clause to a quadratic system mod 2. Okay, so instead of the linear inequalities that we had before, now we will have quadratic system mod 2. So again we'll do this by an example instead of going through the formal proof. So the clause x1 or x2 bar or x3, what do you want to do? You want to convert this into a quadratic equation mod 2, right? So clause convert it to, yeah, so this is trickier than what we did before. What we'll do here is we'll actually so when x1 is 1, we capture it by x1 minus 1, right, being 0. So let's first capture that. So either there is a solution to this, which means that either x1 is 1 or z is 0. If z is 0, then we have to rely on the remaining part, which is x2 bar and x3. So we write it as 1 minus x2 times x2 times 1 minus x3. Right. So either x1 is 1 or z is 0. If z is 0, then either x2 has to be 1. Oh, sorry, either x2 has to be 0, which makes the clause satisfiable because x2 bar becomes true, or x3 is 1, which again makes the clause satisfiable, right? So all these cases are covered. And you can see that these two equations, they are quadratic mod 2. So this clause is true if and only if the system has a root. Right, there is this if and only if condition. And you do this for every clause in your 3C and F phi, and you will just get roughly double the number of quadratic equations. Variables will at most double. If there are n variables, at most you will get actually n plus the number of clauses, many variables. So variables don't blow up too much, number of equations doesn't blow too much, and you have what you wanted. So similarly, phi is in SAT if and only if and only if the corresponding quadratic system has a root. Right, so that implies that you have reduced 3 SAT. Remember, every formula we are creating a system, right? Just one system is being created. So this is a polytime carp reduction to quadratic equation 2. So that finishes the proof of the proposition that polynomial system solving is also NP-hard. But we have done it only mod 2, so you can also try the same trick over other fields. I leave it as an exercise. So how about quadratic equation solving over other fields? Which means finite fields, field of rationals, field of reals, complex, and so on. Right, so pick your favorite field and see what you can do with this proof. So this proof should generalize and give you NP-hardness. And if you can guarantee that the solutions are small, then NP-completeness. Okay, so you'll get either NP-hard or NP-complete depending on what the field is, what your system is. Okay, so let us now move forward. So we have done complexity classes P and NP. So Turing machines and NDTMs. Now we can play with the complexity classes, create more complexity classes. First trick is the co-operator, we call it co-classes. So for language L, we define the co-problem as L complement as just the complement, what it suggests. Right. So for a language L, the co-problem is complement of it. That's simple. And then for a complexity class, you can take the languages, complement them, define a new complexity class. That's the co-class. So this gives us co-classes as co-NP will be what? So co-NP will be the set of L's such that L complement is in NP. Right? In other words, you take languages in NP, complement them, and that's co-NP. So you can do this operation with any complexity class. So you can do it with P, and then what happens? So think about that. So here interpretation is, so for a language L in co-NP, it is easy to verify so for NP it was easy to verify whether it's a yes string with a certificate, given a certificate. Here it will be easy to verify whether it's whether our input is a no string given the certificate. So yes becomes no. X not NL given X and a certificate. Okay, so that's the difference between NP and co-NP. For NP, a solution can be verified. For co-NP, a non-solution can be verified. Right, so it's simple, but at the level of complexity class, it might be a bit confusing. So the question, for example, you can ask here is, what is the hardest problem in co-NP? So what's the hardest problem in KONP. Like SAT, 3 SAT was hardest problem in NP. So 3 SAT complement is automatically the hardest problem in KONP. But we can come up with a better example, a more natural sounding definition, which is tautology. So tautology is as the name suggests, these are formulas which are true, okay, like theorems. So tautology is the set of those CNF, or in fact now it will be DNF. So phi is DNF formula and is a tautology. Tautology is just another fancy word for a theorem, okay, something which is true. But this is just using and or not operators. So it's a simple propositional formula. It's in DNF form. Think of it as complement of CNF. So for NP it was CNF. Now for KONP we are talking about DNF, and it's true no matter how you fix the variables. So claim is that this is the hardest. That tautology is KONP complete. Right, which means which is another way of saying that tautology is in KONP, and every problem in KONP efficiently reduces, so polytime KARP reduces to tautology. So given DNF phi, we consider CNF negation phi. Right, so disjunctive normal form, it's the disjunction of conjunctions, that is what phi was. When you do negation, you can write it as a conjunctive normal form. Let me just give a small example here. So DNF, if you have, let's say, x1 and x2 or x3, so when you take negation, do negation of this DNF, what do you get? You get x1 complement or x2 complement and x3 complement. So this is what I meant. Okay, so you start with a DNF, disjunctive normal form. When you take negation, then it becomes a CNF. Right, so OR of ANDs, AND of ORs. And the property is that negation phi is satisfiable. So negation phi has a satisfying assignment, right? It means that negation phi becomes true, which means phi becomes false, which means that phi cannot be a tautology. Okay, this is an immediate observation. So which means that tautology is in KONP. Right, so in fact let me do this step by step. So we have shown that the no strings of tautology, they have verifiers, which means that we have shown tautology is in NP, right, which means that tautology is in co-NP. Right, that's what we have shown. These things are equivalent. All these statements are equivalent. So just by this negation operator, you can see that what was SAT for NP, now it is tautology for co-NP. But why is tautology co-NP hard, right? That we have to now check, or we have to prove. So the co-NP hardness part. Let's go over that. So let L be in co-NP. We have to reduce it to tautology. So it means that there exists a polytime Turing machine M such that every no string X can be verified. For some constant C, there is a certificate of length x, size of x to the C. Such that M x comma u is 1. And now for this Turing machine computation where u is the unknown, you do Cook-Levin reduction proof and you will get a formula. So now Cook-Levin's reduction on M gives a CNF phi x u such that what happens? Such that x is not in L if and only if phi x u is satisfiable. Right. So no string, there will be a certificate u accepting path which such that M accepts x. So this formula will become 1 phi x u at u. Right. That is what we have from Cook-Levin, and which means what? So which means that x is in L if and only if phi x u is, so we are taking negation, right? Phi x u is not in SAT, which means it is unsatisfiable. But when is a formula unsatisfiable? It means that the negation of it is true, right? If there is no satisfying assignment, which means on every assignment it's false, so negation is always true. So negation is a tautology. Right. So x is in L if and only if negation phi x u is a tautology, which means that we have reduced the problem L, which we started with, from co-NP, we have reduced it to this specific problem tautology. So which means that tautology is co-NP complete. right? So it's not a hard proof, but you still have to go through it just to see how these things are done. So we have now two notions for NP completeness, which is 3 sat, and then any problem to which you can reduce 3 sat to becomes also NP hard. And the second concept is co-NP completeness, which is tautology, and then any problem which you can reduce tautology to becomes also co-NP hard. And the open question is whether these two concepts are the same. So is NP different from co-NP? Okay, so are these two, in fact these two complexity classes, are they the same? Which is equivalent to asking whether tautology is in NP. Which is also equivalent to asking whether SAT is in co-NP. Right? These are all the same questions, because if tautology goes inside NP, then everything in co-NP goes inside NP. So co-NP becomes equal to NP. If SAT is in a co-NP, then whole of NP is in co-NP, so they become equal. Okay, so whether all these concepts, are they the same or are they different? That's the open question. Also, if it turns out that co-NP and NP are the same, then one can study polynomial systems better. Right. So remember that polynomial systems, finding a root, that's an NP hard problem. And so if co-NP becomes equal to NP, then you are saying, it's basically implying that whether a polynomial system, it has a root that has a verifier, it doesn't have a root that also has a verifier. Right. So somehow in this exponential space, somehow weirdly the search you will understand better, okay, if co-NP is equal to NP. So it will also have algebraic consequences if you can show these two equal. Although we conjecture that, usually we conjecture that they are different. Now some easy propositions. So P is equal to co-P. Okay, if you think about co-P, there it doesn't matter whether you are asking yes string, no string, everything is solvable in polynomial time. So P and co-P are the same classes. And compared to NP intersection co-NP, both of them are contained, right? P is contained in NP and P is also contained in co-NP. So they are in the intersection. That's easy to see. And if P and NP are the same, then NP and co-NP will also be the same because of P equal to co-P. So which also means that if you show that NP and co-NP are different, right, if they are different, then P and NP is also different. So the open question of PNP is contained here. Okay, and what is NP union co-NP? So NP you can solve by, you can find the certificate in exponential time, right? We have seen that. So any of these you can solve in exp. That's an upper bound. Yes, these are the simple observations.